But I'm not giving up, giving up now. I'm not giving up, giving up now. I'm not giving up, giving up, giving up on you.
Hello, welcome to another episode of Green's Chemistry Shorts. Today I will teach you a shortcut to understand, or at least create a structure for the electronic geometry and also the molecular geometry. Because those terms are relatively long and we need enough space to create this molecule, I shortened electronic geometry to EG and molecular geometry to MG. Okay? So, for our first example, carbon tetrafluoride. Okay? A very simple way to create the electronic geometry is simply to take the number of valence electrons from carbon and the number of bonds that it's going to make with the terminal atoms. Okay? If you have a periodic table handy, you'll know that carbon is in group 4A. Group 4A atoms typically have 4 valence electrons. Okay? As you can see for the chemical formula here, we have 4 bonds going to fluorine. So 4 valence electrons plus 4 bonds gives you the octet that you so desire. Okay? So you have 8 valence electrons now around the central atom. Okay? Once you divide that by 2, you'll have your number of charge clouds, okay, in order to get your electronic geometry. So in this case, 4 plus 4 is 8 divided by 2, you have 4 charge clouds. The 4 charge cloud case is pretty standard. Okay? Every time we have 4 charge clouds, the electronic geometry is going to be tetrahedral. Okay? Okay? If you need this structure actually drawn, okay, you can just simply do this. So the wedges actually give you the illusion that this terminal atom is coming out of the plane of the board, whereas these hashed lines give you the illusion that an atom is going behind the plane of the board. We don't have hydrogen, we actually have fluorine. My apologies. Now I'm going to draw my lone electrons around the terminal atoms. Okay, so here's our tetrahedral electronic geometry. And if you notice, there are no lone pairs of electrons on the central atom. So that means that the molecular geometry is the same as the electronic geometry. So here, our structure is also tetrahedral. Okay. All right, for our next example, we have the molecule NF3. Okay, similar to CF4, we will come up with the Lewis structure or the electronic geometry for this molecule. Okay, so for nitrogen, nitrogen is in group 5A, so it has 5 valence electrons. You're also going to make 3 bonds with fluorine. 5 plus 3 is 8. Okay, 8 divided by 2, that gives you 4. So we still have 4 charge clouds around the central atom. Okay? Okay? We're going to make 3 bonds. If you remember the Lewis structure for nitrogen, know that you have a lone pair here, 1, 2, 3. So these electrons here are available for another nonmetal to accept for bonding. And that's the case what's happening here for fluorine. Okay? The electronic geometry, since we know that we have 4 charge clouds, it's going to be tetrahedral. Okay. The molecular geometry, however, is going to differ. Why? Because we have 4 charge clouds, but only 3 bonded atoms. So that means that nitrogen is going to have a lone pair of electrons on the central atom. Okay? So, with that being said, for the molecular geometry, it's not going to be tetrahedral. What you'll find is, I'm going to erase this just so I can have better clarity. So nitrogen here, we have our lone pair. And I'm going to draw it just like I did this carbon tetrafluoride. We have the fluorine bond within the plane of the board. This fluorine bond coming out of the plane of the board toward you. And this fluorine bond going behind the plane of the board. Can't forget our lone pairs. Okay, so what we have here is a structure called a trigonal pyramid, or a 3-sided pyramid. Okay. If you notice, nitrogen is the very top of the pyramid. Okay, so these are 2 cases in which we have 4 charged clouds. However, the electronic geometry and the molecular geometry for NF3, and this also works with ammonia, and it does not match, so we have to adjust. Okay, so the molecular geometry here is Trigonal Pyramidal, or having a trigonal pyramid. Okay, we have Tellurium Tetrafluoride. Okay, now if you compare this formula to the carbon tetrafluoride, it looks like it should have the same structure, but not so fast. So you have to look for these deviations, or it may seem like I'm tricking you on a test, but we're following the same process. Okay? Tellurium is actually in group 6A. Okay, group 6A. It's going to make 4 bonds with fluorine. 6 plus 4 is 10. Okay? 10 divided by 2 is 5. So this is the 5 charge cloud case. Okay? The 5 charge cloud case for tellurium yields an electronic geometry of Trigonal Bi-Pyramidal. Okay? The Trigonal Bi-Pyramidal structure gives us 2 axial positions and then 3 equatorial positions. Okay? All right, so we have 4 bonds with fluorine, but we have what? 5 charge clouds available. So that means that one of these positions is going to be occupied by a lone pair of electrons. Okay? As it turns out, the lone pair of electrons in all 5 charge cloud cases goes along the equatorial region of the structure. We can have fluorine occupy both axial positions. And also 2 equatorial positions. The other equatorial position can occupy a lone pair. Okay? Let's not forget our lone pairs of electrons around the terminal atoms. Okay? So here, the electronic geometry is Trigonal Bi-Pyramidal. The molecular geometry is not trigonal bipyramidal. It's actually a structure that we call a seesaw. Okay. If you rotate this molecule on its side, you can see where you have the fluorines acting as if they're people on a seesaw, and it'll rock back and forth. But I mentioned that to you in class. Okay? Last but certainly not least, we have the molecule IF3. Okay? And if you were paying any attention to this video, you notice that what? Iodine is in group 7A. It's making 3 bonds with fluorine. 7 plus 3, of course, is what? 10. 10 divided by 2 is 5. So we have another case where we have a 5 charge cloud electronic geometry, meaning that the electronic geometry will be, again, trigonal bipyramidal. Okay. I'll do the same thing here, where we have iodine. Okay, but we only have 3 bonds with fluorine. So I'll make sure that the fluorines occupy the axial positions and 1 of the equatorial positions. Okay, so that means that we have 2 lone pairs along the on the central atom. Okay, and these 2 lone pairs are going to occupy the equatorial region. So we have a pair there, and also a pair here. Okay, now if we only focus on the bonded atoms, the bonded atom arrangement, we'll see that the molecular geometry is something that we call T-shaped. T-shaped. Because if you rotate it 90 degrees, it looks like a T. Ooh. Anyway, so hopefully you gained something from this, this short video. Okay, let us recap. Just because the chemical formula looks a certain way doesn't necessarily mean that you're going to have the same type of bond arrangement all the time. Okay, so just because you have 4 terminal atoms doesn't mean that you have the same structure. You have to consider the fact that different central atoms can accommodate a different number of valence electrons. Okay, this obeys the octet rule. This molecule also obeys the octet rule. These 2 molecules, we have the octet rule is not necessarily followed. We have an expanded valence, okay, for 10 electrons around the central atom apiece. Okay? So, that's it. You've just been shorted.